The following content is provided by MIT OpenCourseWare under a Creative Commons license. Additional information about our license and MIT OpenCourseWare in general is available at ocw.mit.edu.
Okay, so where were we last time? Last time we said we were setting aside the problem of the structure of the atom. We're setting it aside because we were stuck. And what we had to do was to look at another area of discussion, and that's this wave-particle duality of light and matter. Because it is that discussion that is going to give us the clues about how to proceed. All right? So we're putting aside the discussion of the structure of the atom all the way till next Wednesday, because next Monday, I was reminded, is a student holiday. Okay? Hey! Hey! Okay. All right, and so we started. We talked about the wave-like properties of light. We said that the property of superposition, the fact that you can put waves at the same point in space and their amplitudes add, since waves have both positive and negative amplitude, that means you have constructive and destructive interference. And it is those interference phenomena, then, that are evidence for wave-like properties. And we did the two-slit experiment to try to give you an example of interference phenomena. And we were trying to understand those interference phenomena. And we did so in terms of this diagram here. You know, the interference phenomena that we saw was an array, or actually a row, of bright spots, dark spots, bright spots, dark spots. Okay? And we drew these semicircles here around each one of the slits. They represent a little bit of the wave that emanated through those slits. Because those slits are small, then those waves emanated equally in all directions. So that's why the semicircles, these semicircles represent the wave maxima. And what we discovered is that if we looked along this line here, this line which led to this bright spot, that all of the waves along this line were constructively interfering. That is, we had the maximum of the two waves at the same point in space, or the minimum of the two waves at the same point in space. And we noticed that everywhere along this line, where we had that constructive interference, the difference in the distance of the waves traveled was 1 lambda. We noticed here that everywhere along this line, that led to a very bright spot, that we had constructive interference, and the difference in the distance traveled by those two waves was 2 lambda. And likewise up here, right? Along this line, the difference in the distance traveled was 0 lambda. And from just that qualitative, or in a sense, qualitative observation, we drew a conclusion. And that conclusion was, in order to get maximum constructive interference, the condition that had to obtain is that the difference in the distance traveled by the two waves has to be an integral multiple of the wavelength. So n could be 0, 1, 2, 3, etc. And so the very bright spot here that's always bisects the two slits, since n is 0, we call that the 0-order interference feature, or the 0-order diffraction feature. The bright spot that is either to the left or to the right, or up or down of that center bright spot, is the first-order diffraction feature, or the first-order interference feature. And then the bright spot that is either up or down, the second bright spot, up or down from the center, is a second-order diffraction feature, and so on, and so on. All right, and in recitation section, what you also should have done is you should have reasoned through what the condition was for destructive interference. That is, in between these bright spots, you have dark spots as a result of destructive interference. And that results because, say, right here, you get a dark spot. Right here at that point, you see the maximum of one wave at the same point in space as the minimum of the other. And so they exactly cancel. And so by just analyzing what waves were interfering, destructively interfering, you should have come up with a general expression for destructive interference of n plus 1/2 times the quantity lambda, that quantity times lambda. That is your general condition for destructive interference, all right? The difference in the distance traveled by the two waves. This kind of diagram here, we're also going to see on Friday, because this interference phenomena is the property associated with waves. And what we're going to do is we're going to see this diagram again when we scatter electrons for particles. We're going to see that particles also will destructively and constructively interfere. They also have wave-like properties, and that's what we'll do on Friday. Okay. So we've established now the wave-like properties of radiation. So I'd like to move on and talk about the evidence for the particle-like nature of radiation. All right. So the evidence for the particle-like nature of radiation comes from an effect called the photoelectric effect. So shortly after Thomson discovered the electron, scientists were noticing that if you took a metal and you shined radiation on that metal, that indeed electrons were emitted. Electrons came off, and these were called photoelectrons. However, the radiation that you shined on the metal had to have a frequency nu that was greater than or equal to some threshold frequency, mu naught. That is, if you took radiation of some frequency here, nu, that was less than this threshold frequency, well, you didn't get any electrons off. Well, another way to kind of understand that data, or that effect, is to just plot the number of electrons that come off as a function of the frequency of the radiation. And so at low frequency, well, there's no electrons, but then all of a sudden you get to nu naught, and then electrons start coming off. And no matter how high you increase the frequency here, the number of electrons that come off remains the same, remains constant. And it turned out that for the metals that were looked at that time, this threshold frequency here, this threshold frequency was in the UV range of the electromagnetic spectrum. Well, in addition to just measuring the number of electrons and generally observing this effect, scientists didn't understand what was going on, so they just started measuring everything they could think about measuring. And one quantity that they measured is the kinetic energy of these electrons that were being emitted. And so you take kinetic energy here, Ke, as a function of the frequency. They found is that at low frequency again, there's no kinetic energy because there are no electrons. And then at some frequency, hey, all of a sudden electrons started coming off. And the kinetic energy of those electrons seemed to increase with the frequency once past that threshold frequency, nu naught. All right. Well, this was really another one of these conundrums here at that time, because classical physics classical electromagnetism, classical physics had no way of explaining these data. And in fact, what classical physics predicted is that the kinetic energy of these electrons, that kinetic energy should have nothing to do with the frequency of the light. That is, the kinetic energy was constant. As you increased the frequency of the light, classical physics would tell you that the kinetic energy shouldn't be affected by the frequency of the light. There was nothing in the classical way of thinking, classical electromagnetism, that connected the frequency of the light to the kind of energy, all right, to the kinetic energy. There was no way for blue light to make the electrons have a larger kinetic energy, and red light, or for blue light to have an effect on the kinetic energy, and red light to not have an effect on the kinetic energy. In addition, what classical physics predicted is that the kinetic energy of the electrons should be dependent on the intensity of the light. That is, the more and more intense the radiation on the metal, the more and more kinetic energy those electrons should have. Because after all, if you increase the intensity of the light going into the metal, you're putting more and more energy into it, and that should be reflected in, just how energetic those electrons were kicked out. Right? The more energy in, hey, the electrons ought to come out with larger and larger kinetic energy. All right, but of course the observation was that the kinetic energy of the electrons had nothing to do with the intensity of light. Right? The kinetic energy of the electrons didn't increase as you made the light brighter and brighter. As you put more and more energy in, the kinetic energy remained the same. Didn't have an effect. Right? So this was a real conundrum here. Just the known classical physics was making predictions really just contrary to what was being observed. All right, so these data here of the kinetic energy versus the frequency, well, these data were around for a few years before Einstein took a look at them in 1905, 100 years ago. And he looked at these data for many different metals. So here's some data for metal A, for example. And here's some data for metal B. And in both cases, it certainly looked like the kinetic energy was linearly dependent on the frequency of the radiation. But what was different for the two different metals was the threshold frequency here, nu naught. All right, so what Einstein did is he went and fitted a straight line to these data, right? Y equal mx plus b, okay? And when he did that, and he went to calculated the slope here, m of these lines, he thought, very interesting, right? Because the slope of those lines was 6.626 times 10 to the minus 34 joule seconds. The slope of those lines was something called Planck's constant, h. Okay, so you say, so what? Well, the reason he was so interested in this is because just a few years earlier, there was a scientist by the name of Max Planck who was interested in understanding what was called the Blackbody radiation data. All right, so what's a black body? Well, let's just for simplicity purposes think of the black body as the burner on an electric stove. what you know is that if you turn up the voltage on that burner, the burner gets hot, increases in temperature. And you increase the temperature, and sooner or later, that burner is glowing a bright red. And you increase the temperature some more, and the burner is glowing a brighter red. And you increase it some more, and it's glowing orange. And you increase it some more, which you shouldn't do, and it's glowing yellow. And then if you could, increase it some more, it's glowing white. All right? So what's happening as you increase the temperature is that the radiation from that black body, this is the black body radiation, is increasing in intensity, but more importantly, the frequency is getting larger and larger. So red, dark red, bright red, orange, yellow, white, that's all frequencies. The frequency is shifting to higher and higher values. And what was actually done at that time is that the intensity of that black body radiation, and this material is not in your notes because you're not responsible for it. I'm just trying to make this surprise that Einstein noticed about the slope. I'm just trying to put it in some context, why he was so surprised and amazed at it. So this black body intensity here, people had dispersed that radiation and looked at the frequencies that were coming off. So this is intensity versus frequency. So here's the general shape of that intensity versus frequency. That was observed for some temperature, T1. That was a low temperature. And then when the temperature was increased and the frequencies, the intensity versus frequency was observed, well, the frequencies generally got higher frequencies. This is higher temperature. Intensity goes up. And you increase the temperature some more, and you get even higher frequency. So T3 is the highest temperature. And that's what the data were. And what Planck was trying to do was to understand the origin of that black body radiation. Excuse me. So what he said is that in these black bodies, in these materials, what there must be are oscillators, right? Oscillators that are giving off this radiation. But he had another little kick to these oscillators. These oscillators were giving off radiation or energy in chunks, in quanta, in particles, okay? And using that idea, plus some statistical mechanics, he was able to calculate the shapes of these curves. That is, he got for the lowest temperature here, if he calculated it, he got a curve that looked like this. And for T2, he got a curve that looked like this. And for T3, he got a curve that looked like this. He got the shape right. But he wanted to get the intensity right, too. And so what he realized he had to do is he essentially needed to have a scaling factor, right? A scaling factor actually in front of his frequencies of his oscillators. He wanted a constant, right? And so he said, what constant do I have to have in order to make all of these data fit the observation? Hey, that constant is Planck's constant, his own, 6.626 times 10 to the minus 34 joule seconds. There it is. That's Planck's constant. That's it. There's nothing deeper here. It is a natural constant. It comes from our observations of the world, of nature, right? That's it. It's a fitting constant. And so that's why Einstein was so amazed here when he realized, hey, you know, this number, it's the same number as what comes out of here. there must be something very fundamental about this H, this Planck's constant. All right? That's the story. Okay, isn't that amazing? All right, so what Einstein then proceeded to do, of course, is to write down the equation that he, tricky to get these boards, they move so fast. He wrote down the equation of the straight line that he just put through these data. And so that equation is the kinetic energy is equal to u, which is our x, h, which is the slope. And then what he found is that the intercept here, the intercept, of course, is minus h times mu naught. So this is plus or minus h times mu naught. Okay, and that's the equation of the straight line. And of course, he realized, hey, if this is energy on this side, boy, there better be energy on this side, right? And so this h times nu better be an energy. And since this nu was the frequency of the incident radiation, well, therefore, h times nu better be the energy of the incident radiation, E sub I. And that's where this expression, energy is equal to h times nu, comes from. Nothing more. That's where it comes from the photoelectric effect. This was the first time that there was any relationship between the frequency of the radiation and the energy of the radiation. In classical electromagnetism, there is no relationship between the frequency and the energy. This was the first time in which that relationship was observed. And so eventually, well, what this is saying is the following. This is saying that you can have any frequency of radiation you want, but the corresponding energy comes in these chunks of h times nu. H is a quantization constant, okay? So radiation, nu, is continuous, but the energy that corresponds to any given frequency of radiation is h times nu. All right, so this E equal h times nu here is thought of as a quantum of energy, a particle of energy, a chunk of energy. Later on, it became the photon, right? The energy of a photon. Okay. Now, so if this h times nu here was an energy, well, this h times nu naught, it also better be an energy. And it's the threshold energy. So let's draw an energy level diagram to try to understand that. So I'm going to plot an energy here. And let's draw an energy level for an electron. This is an electron here bound to the metal. And we know that it takes some energy to rip this electron off of the metal. So up here at higher energy is going to be our free electron. I'll just call it electron free, not bound to the metal anymore. And the energy that is required to pull the electron off from the bound state to its free state, this energy here is this threshold energy, h times nu naught. Right? This threshold energy is like an ionization potential. You know what the ionization potential is, just the energy required to pull an electron off an atom or a molecule. However, when we're pulling an electron off of a chunk of a metal, we actually have another name for it, and it's called the work function. That's just historical, right? But it's the same thing as an ionization potential. And we often give it the symbol phi. So that threshold energy, ionization energy for a metal, is the work function here, H times mu I. All right. So the important point here is this. In order to get an electron off of the metal, what you have to have is you have to have energy E sub I. That energy E sub I has to be equal to at least the threshold energy, H times mu naught. If you come in with energy of this radiation, of this wavelength, and that frequency, right, you pull the electron off, and then the electron is off the metal, and it just kind of stays there, doesn't move away. Okay? But you can also come in with energy here, E sub I, that is greater than this work function, than the threshold energy. And you can pull the electron off, but then the electron is actually going to move away from the metal, and the energy with which it moves away from the metal, its kinetic energy, is just the incident energy minus this threshold energy. It's the excess energy here. I'm going to write it as the kinetic energy. Okay? All right, so from that energy level diagram, right, this energy, the incident energy, has to be equal to the work function, H nu naught, plus the kinetic energy. Or if I turn this around, the kinetic energy is equal to the incident energy minus H nu naught. Okay? The actual expression for the energy that Einstein found. I just turned that equation around. All right? This is an equation that you have to know. All right? I won't give this to you on an exam. Now, you don't have to memorize it. You just have to reason it. Draw yourself an energy diagram. You know conservation of energy. The sum of these two energies has to equal the incident energy. Okay? Then you'll be all set. Now, what's very important here is the following. And that is that if I come in with radiation that is, say, a half of the threshold energy. So suppose I come in with 2 photons, where each photon is 1/2 h nu. The bottom line is that you're not going to get an electron off, all right? Even though you're coming in with 2 photons, which together are going to give you the threshold energy, you won't get a photon off. You have to come in with at least the energy of the work function. A photon has to have at least this energy to get an electron off. That is the particle-like nature of radiation. That energy comes in chunks, in particles of energy, right? In quanta of energy. And likewise, if I came in here with a photon that had twice the energy of the work function, or the threshold energy, I would still only get 1 electron off. I would not get 2 electrons off, even though energetically you would be able, in principle, to get 2 electrons off. But you won't. You'll only get 1 electron off. So whenever you send a photon in, if it has enough energy, that is, if its energy is equal to or greater than the electron, than the work function, you'll get an electron off. So there's 1 electron for every photon. Never get 2 electrons for every photon. All right? Or you can never get 1 electron for 2 photons that are lower energy. That's the particle quantum nature of radiation. All right? That's important. Yes? I'm sorry? What is the form of the photon? Yeah. What do you mean by form? Oh, you want a picture. Yeah, you want a picture of the photon. Yeah. You know, you can't, right, you're looking at them. You can't draw a picture of the photon, right? Because you want to relate it to something that is within your classical experience, right? And you can't do that, right? It isn't a, it isn't a classical particle, right? And that's what you're working with right here, right? That's what you're trying to use your experiences that are everyday experiences to explain something that isn't within your everyday experiences. You know, you don't have a frame or a format to do that. Okay? Yeah.
How often are the electrons conducted if you have like an electromagnetic wave or something coming out? Like, does it come off just at a constant speed?
Yes, right. If you have a constant flux of electrons onto the surface, you will have a constant flux of photons onto the surface. You'll have a constant flux of electrons. Now, there's a probability, right? It's not necessarily the case that every photon gets in will eject electrons, because there are other kinds of competing processes.
But at what rate do they come off?
Whatever the rate with which the photons come in.
So that just depends on like...
It depends on the flux of the photons, right?
Okay.
Right. And we will have some problems like that, okay? Where we're going to assume that the probability of the electron coming off is going to be 1. So at 1 electron for every photon. But in reality, there are competing processes, okay? Are all electrons being ejected? Actually, some electrons, and again, this goes to the probability, some are actually kind of going in, too, right, into deeper the metal.
The probability is not affected by either ion.
Not the probability, right. Right. The rate of which the electrons come out with is dependent on the intensity. So the more photons you send in, the larger the number of photons per second coming in, the larger number of electrons per second coming out. Okay, this is a plot here of the energy of the electrons. Yeah, right. Okay, that's all right. Okay? Other questions? Yeah. Yeah, eventually, yes, absolutely. There's other problems that will come in. Usually, your light source isn't so energetic that you could possibly do that. Now, also, usually what happens is that you've got your metal grounded so that as you lose electrons, new electrons come into your, and fill it up to the Fermi level, okay? And so you don't charge up your sample. But in an experiment, if you had your metal just not grounded and you did shine some radiation, what would happen is the metal would start to charge up. And then that will make it difficult to get electrons off. Okay. Yes? I'm sorry?
The threshold energy changes based on the metal, right?
Yes.
Based on what, just how weak they charge in the metal, or?
How strongly those electrons are bound to the metal depends on the electronic structure of the metal. And we're going to talk a little bit about what determines the strength of the interaction for electrons on atoms and molecules, but it's similar to what it is for metals. That's coming in a few days. Yes? Oh, yes, there is, right. No, you don't actually have to have a metal. You could do it. They're usually higher frequencies on insulators and semiconductors, right? It's harder to see the effect, but it can be done and has been done, right? Okay? Okay. Well, what I want to do right now is to show you an experiment we're going to do. We're going to do a photoelectron experiment. All right. And the experiment is this. We've got a device up here. As the lights go down. All right. What we've got is an aluminum plate. And that aluminum plate is mounted on this blue metal rod. And in the middle of this rod is a needle on a pivot. And this is a fairly frictionless pivot. And this black ring here is just a support structure. It's an insulating support structure. And what we're going to do is we're going to put some excess charge on this aluminum plate. And that excess charge is going to run down this metal rod and then onto this needle. And because that excess charge, the electrons on the needle and electrons on the metal rod, they are repulsive. Since this is rather frictionless, hey, that needle is going to move because of the repulsive interactions between these electrons. What we're then going to do is we're going to try to do the photoelectron experiment. We're going to take some UV radiation and shine it on this metal and drive the electrons off. And we should see then the needle swing back to its original position. Okay, I need a couple of volunteers in order to do this experiment here. Okay, come on. Okay, one of you, come on up. All right, fantastic. Yeah, I think that's, all right, good. Yeah, okay, one of you needs to be the charger, and the other needs to be the discharger. Which one?
Discharge.
You want to you want to discharge?
Discharge.
Discharge. Okay, so you come over here. All right. And what you're going to do is you're going to, it's on, okay. You're going to discharge the aluminum plate after we get some excess charge on it. You're going to do it just by holding it up to here. Okay, you have to get it kind of close because it's not a very intense UV source. Okay? All right. So could you get the video cam on the side or on the center? I forget where we're putting it. I guess we're putting it on the side, right? Okay. There we go. Okay, there's the device. All right, so you're the charger. So what you got to do, what we're going to do to get the excess charge, we're taking a piece of fur, natural fur, and yeah. All right. And we're going to rub it on this lucite rod, all right? And you've got to keep your fingers on the yellow tape here, okay? And we're going to transfer some of the natural oils here onto this rod. And there are plenty of negative ions around here and free electrons. And that oil likes those negative charges. And so there are going to be excess negative charges on this lucite rod. And then you're going to come over here and just touch the edge of this and let the electrons flow onto there, okay? All right, so you gotta, are you right hand? Okay, you got to rub that really hard, all right? Really hard, really hard. Okay, great. Go over there, touch the end. Hey, whoa, cool. Okay, why don't you give it another jolt here? We'll really move that needle over. Okay. Ooh, okay, discharger. Can you? Whoops. Okay. We gotta give it another jolt. You can't. Yeah, it's okay. You may have touched it with something else and discharged it a little bit. So no, that's okay. You gotta get the hang of this here. Okay. All right, really hard. All right, good. All All right, fantastic. Okay, take it off, take it off. That's what it is. You're holding it on to, oh, okay, that's pretty good. All right, put it in front there, get it a little bit closer. Here comes the UV radiation. Whoa, we did it. All right, try it again, try it again. All right, really hard, just touch it. All right, take it off. All right, do it again. You'll need to do it again. You got to get it right here. Not too much, not too little. Hey, okay. Oh, okay. Oh, hey, it's doing it. All right, discharger in front. Hey, electrons off. Okay, now we got to do a control experiment. All right, and that is you got to charge it up again. But now, when you put the light there, what I'm going to do is I'm going to hold up a Pyrex plate in between the light and the metal, and it's going to block the radiation, and it shouldn't discharge, right? Okay. All right, so you need to get on there. All right, fantastic. Ah, good. All right. Oh, okay, geez. Oh, there it goes. All right. Here's the plate. Hey, get it a little bit lower, do a good discharge. Yay! Not good. Fantastic. Thank you very much. Thank you for being a good sport. All right, great. Okay, so that's the photoelectron experiment. Hey, it works. Okay. Okay. Well, what I wanted to do now is just to spend a few minutes working on a few problems. I think these are pretty straightforward, but I just want to make sure that everybody's on the same page here in terms of being able to do the homework. All right, so here's the first problem. First problem says, how many photons? And remember what we said a photon was. E equal h nu. This is the number of joules. Implied is the number of joules per photon. Although we don't usually write this, but that's what that is, joules per photon. You may want to write it as you do these problems. So how many photons which have, how many photons associated with radiation of a wavelength lambda equal 1 picometer, which is 1.0 times 10 to the minus 12 meters. How many of these do you need in order to create, say, a laser pulse of energy that's 1 joule? All right, so lasers are pulsed. So I'm talking about a pulse of energy 1 joule, okay? So you want to draw yourself a picture here? We're drawing a picture of 1 pulse of energy, right? 1 joule, right? Now, we haven't been given the frequency here of this radiation, but we know the wavelength, and we know the relationship between frequency and wavelength. It's just C over lambda, right? So I know what lambda is. I can calculate mu. And when I do that, I find that the energy of the photon, hc over lambda, that energy of the photon is 1.99 times 10 to the minus 13 joules per photon. And I'm using one more figure than is significant since this is an intermediate step in the calculation. Okay, so if I want 1 joule, a pulse of 1 joule of energy, and I'm asked how many photons do I need to get that, and each photon is 1.99 times 10 to the minus 13 joules, well, that means that I'm going to need 5.0 times 10 to the 12 photons. Okay? Okay, there was a question here? Okay. All right. Let's work another one. And here we want to define what we mean by power. All right? This says the power of radiation from a continuous laser is 3 milliwatts. So we've got some laser, And the power coming out, the power of that radiation coming out is 3 milliwatts. Well, what is power? Power is energy per unit time, right? It's the energy delivered or the energy expended per unit time. The unit of power that we're going to use is a watt. A watt is a joule per second. Right? So we're told that we have radiation of 3 milliwatts. That's 3.0 times 10 to the minus 3 joules per second. And the question asks, how long will it take for a total energy of 1 joule to be supplied? Okay, well, 1 joule, and we have the energy, the rate of energy supply as 3 times 10 to the minus 3 joules per second. And that gives us 330 seconds. Okay, so that's straightforward. Okay, and then finally, yes. Oh, okay, sorry, yeah, thank you. All right. And then finally, got one more. It says how many photons per second of, again, the same radiation, the wavelength of 1 picometer. So that means, we're dealing with photons that have an energy of 1.99 times 10 to the minus 13 joules per photon. So how many photons per second, the rate of photons at that wavelength, do you have to have if, or do you have if the power of the radiation is 3 milliwatts? Well, the power of the radiation is 3.0 times 10 to the minus 3 joules per second. Okay. And we have 1.99 times 10 to the minus 13 joules per photon. So in order to have this kind of power, right, what we have to have being emitted is 1.5 times 10 to the 10 photons per second. Okay? Okay. All right, so the photoelectric effect is one of the experiments that demonstrated the particle-like nature of light, of radiation. Particle-like nature, because you have to have these chunks of energy to make some process occur. Next time, we're going to look at, and we'll just talk briefly about the other experiments that demonstrated the particle-like nature of radiation. And that other experiment is the demonstration that a photon has momentum, even though it doesn't have any mass. Okay? See you Wednesday. See you Friday.